Okay, so where we left off in our last video is we saw that when we had a production function that looked like this, right? L to the 1/2 times k to the 1/2. We got a cost function that told us that no matter how much output we're producing, an extra unit of output is always going to cost us 20 bucks. And that's not necessarily, in some circumstances, this might be a great description of reality, but in others it might not be, right? We can imagine lots of business situations where, let's say you're a restaurant, you decide to franchise, right? Have 2 or 3 or 4 locations. The more locations you have, potentially the more levels of management you're going to need to keep track of everything, right? And keep everyone on the same page. You could imagine your costs going up. On the other hand, let's say that you're something like a auto parts or a car manufacturer. It might be that the cost of setting up a whole factory to produce a small number of cars, right, 100,000 cars or 1,000 cars, might be much higher per car than if you were producing 1,000,000 cars. If we imagine you're something like Microsoft, right, you could imagine that you have almost the same costs of producing a single copy of Windows than of producing 1,000,000,000 copies of Windows, right? So your cost per unit would be decreasing dramatically as you increase your scale. So we need a language, we need to have some mathematical understanding of this idea we're going to talk about as economies of scale. So to think about this, let's say that instead of saying L to the 1/2 k to the 1/2, let's say that I had the production function L to the 1/4 times k to the 1/4. Still had wage rate of 20, rental rate of 5. Right? So now my MRTS would be what? Still dFdL over dFdk. But now dFdL is going to be 1/4 L and minus 3/4 k to the 1/4, right? dFdk is going to equal 1/4 L to the 1/4 k to the minus 3/4, right? So if I take this ratio, I'll still get k over L, just like before. So if I say MRTS equals price ratio, that's just going to give me, again, k over L equals W over R, right? K is going to equal W over R times L. But now when I plug this into my isoquant, I'll get right? WL, I'm sorry, what am I doing? I'll get L to the 1/4, k to the 1/4 equals Q, right? Which is going to tell me L to the 1/4, this is of course 4L, times 4L to the 1/4 equals Q. So L to the 1/2 is going to equal Q over root 2. L is going to equal, L of Q is going to equal Q squared over 2. K of Q is going to equal 2Q squared. And my cost function, C of Q, is going to equal 20 times Q squared over 2 plus 5 times 2Q squared is going to equal, right, 20 times Q squared. So in this case, right, with this slightly different production function, if I wanted to double output, that would more than double costs, right? I would increase my costs by 4 times rather than by doubling costs. Now, I want you to notice for a minute the ways in which this production function in this situation is and is not equivalent to this situation we just talked about. So as you notice, right, as we saw when we worked through this, our MRTS is exactly the same, right, with L to the 1/4 times k to the 1/4 as with L times k, for exactly the same reason that our MRS would be the same if these were utility functions, right? One's a monotone transformation of the other. What that means is, if I wanted to draw isoquants, they would look exactly the same, right? I could still have an isoquant where 16 and 1, so equivalent to 1 and 16, right, is equivalent to 4 and 4. However, this would have been the isoquant, right, with L to the 1/2 times K to the 1/2. This would be the isoquant representing output of 4. Right now it's going to represent the output of 16 to the 1/4, so this is going to be Q equals 2. The other important thing, though, is let's say that I wanted to increase output from 2 to 3. Right? So I would need L times K to equal 3 to the 4th. Right? And 3 to the 4th is going to be 81. So if I needed 4 and 4 before, now I would need 9 and 9. Right? If I wanted an output of 4, I would need 16 and 16. Right? Whereas if I only wanted an output of 1, I would just need 1 and 1. So what's happening is the distance between each of my isoquants is growing, right? Right, I have to increase both inputs by 3 to get from an output of 1 to an output of 2. Then I have to increase both inputs by 5 to get to an output of 3. Then increase them both by 7 to get to an output of 4. Right? So the costs of increasing production are getting larger and larger. As a result, isoquants that represent the same increase in production are going to get more and more and more distant from each other. Whereas before they would have been exactly the same distance apart. So we're going to call this whole set of circumstances decreasing returns to scale. The basic definition is going to come from here. It's going to come from the idea that the marginal cost of production, that is the degree to which an extra unit of production is going to increase my costs, gets larger as production increases. Cost per unit, larger as output increases. The result is going to be isoquants increasingly distant from each other. And an easy way to test for this, that isn't true 100% of the time, but will be true 100% of the time that I make you do this, is if we double inputs, outputs will less than double. Cool. So that's decreasing returns to scale, but of course we could have increasing returns to scale too, right? Let's say that we had f of L and K equals just L times K. We'd still have an MRTS of K over L, right? We would still have, with our input costs, K equals 4L. But then when we said L times K equals Q, L times 4L equals Q, we would end up saying that L squared equals Q over 4, right? L would equal root Q over 2. K would equal 2 root Q, right? And our cost function would be 20 times root Q over 2 plus 5 times 2 root Q would be 20 root Q. So what does that mean? It means that if I produce 10 units of output, or bad example, if I produced 4 units of output, right, my cost would be 20 times 2 would be 40. If I wanted to then produce 9 units of output, my costs would be 20 times 3 is 60, right? So I would more than double my output, and I would only increase my cost by 50%. And in this case, for equivalent reasons to the last case, if we drew our isoquants, they would get closer and closer together as I increased my output. Right, so for increasing returns to scale, it's going to be the opposite of decreasing returns to scale. Cost per unit is going to fall as output increases, and isoquants are going to get closer together. Cost per unit decreases as we produce more units. Production increases, and isoquants increasingly close. We can find increasing returns to scale by seeing whether doubling inputs less than doubles or more than doubles output. Right, so for example, with L times K, right, f of 2L and 2K would equal 2L times 2K equals 4 times LK. Okay, fantastic. Looking forward to talking to you guys about this in class. Thank you so much for bearing with me.